in designing the systems from scratch. That is what is his greatness, because he starts from the scratch and basic ideas and develops it into a space technology. That is the practical knowledge he had now. That will help our young professionals to get a lot of ideas from him, and this talk is going to be enriched in a different way, because he may be explaining a lot of practical things to do and theoretical as well as how to go for a system design, how to innovate, how to design a system that he may be explaining in this talk. Moreover, he is having a lot of ideas. He is sharing a lot of ideas, innovations, ideas that helps society to empower the society. A lot of ideas he already had in his mind. I know very well his ideas and all. In that sense, also, our young professionals can approach him to get the guidance, get the knowledge, and what areas we have to focus, what way we have to focus. And that he is a very approachable person. So take the benefits of all these connections, get much more out of this talk, as well as in personal relationship with Mr. Hemachandran. So this talk is going to enrich our knowledge, our professional community. I welcome you to this different and enlightening talk. Thank you, Hemachandran. Thanks once again, and thanks for accepting our invitation and giving a talk to our young professionals. Thanks a lot.
Thank you, sir. Now, I would like to call Dr. Chinmoy Saha, founder and immediate past chair of MTTS, past chair of APS, and regional coordinator of AP Society, to say a few words. Over to you, sir.
Thank you, Anuswara. I don't want to take much time because we are waiting for a very exciting talk by a very seasoned expert. I welcome Dr. Hemachandran. He brings a lot of experience and expertise, as already outlined by Dr. Apren. And thanks to Dr. Apren and the new committee of the MTTS Kerala chapter. Just few words I'll share because start as soon as possible. We hear a lot about academia and industry, the gap between academia and industry. So today's speaker is actually from industry. He has spent almost whole his life, more than 3 decades, in an Indian space research organization, and he has done, demonstrated, and executed various live projects related to GNSS technology and its applications. And when a person like Dr. Hemachandran talks in this type of forum, this is a real opportunity for the academicians like us, the young students also, to understand the little difference, the more challenge that industry research demands over the academic research. And I am sure this talk will benefit all of you. And in fact, current positions, the current office bearers of MTTS Kerala chapter is also a very nice blend of academia and industry. Our current chair, Dr. Apren, has been in the industry. He has been in academics also as a visiting faculty at ISRO Trivandrum. He has served as a seasoned expert in different responsible positions in BSCC. We have Mr. Orijit, who is also from industry. And we have Dr. Shukamal De, professor at IIT Palakkad, who is from academics. So we want to bring a nice blend and a mix of academia and industry, because this is the demand from the time, and this is what the students also should learn. I mean, their academics, their technical knowledge finally should be applied for academic research as well as for patents, publications, and then real applications, because now government of India is talking about various new initiatives, Make in India, so we have to minimize the gap of research between academics and industry. I am sure this talk is going to be very, very useful for young students. A lot of participants even on the weekend. And as you have seen over the last 2.5 years, we are still continuing our program, various programs, workshops, helpful talks, talks like this with experts from industry. So we continue this endeavor. Once again, thanks to Dr. Hemachandran and my office bearers for taking this initiative, and also to the students who are the real pillar for our chapter. Thank you very much. I'm sure this talk is going to be very much exciting, and we'll definitely contemplate on the points Dr. Hemachandran is going to talk about, and it will definitely grow. Thank you. Over to you. Sure.
I'm inviting Hemachandran sir to take the session.
Okay. Good evening to all.
I think
We thank
the
Ms.
speaker.
Anasura for. Are you able to listen?
Okay, sir, you may start. I think already our volunteer has given a brief bio of the speaker. So just before starting, I want to say that it's a very great opportunity for all of us, especially for the participants. You try to make it an interactive session, and there will be a question and answer session after this talk. So you participate, and once again, we welcome our speaker. So you please, you may enlighten us with your talk. We are eagerly waiting.
Okay.
You can just maybe
again,
put
good
your
evening
slides
to all.
into.
I hope you are able to listen.
Yes, sir.
Yeah.
You may put your slides in that view mode.
Okay. Are you getting now?
Still not getting, sir. It's
Go to
Just wait.
slideshow.
slideshow. Just
Yeah, it's in slideshow only.
I suggest one thing: you stop sharing first.
Okay.
Now you start sharing, and when you start sharing, you share screen.
Okay.
Don't share any particular app. You share your entire
Okay.
screen.
Okay. Yeah. Now it's okay.
No, not yet.
Now, earlier you could see the slides.
yeah, we could.
Yeah, I confirmed. No. That time.
Yeah. Now, are you sharing screen, sir?
Yeah, I changed to screen sharing.
Yes. Maybe just stop and stop
Again.
and again share again.
Just wait. I think it's getting connected. No, before the start around 7 o'clock, we checked and the PPT was getting.
Yeah, it was getting.
Shall I log out and come inside once again?
Okay, sir. Try. We're waiting.
One thing, one suggestion I have,
The problem you are facing?
Hemachandran, one minute.
Yeah. I shared everything, but I don't know why.
Hemachandran, you can you do one thing?
Yeah.
Get Arjit's mail ID and share that presentation can be shared to Arjit.
But that is okay, but that will be a delayed process and he won't
Okay.
be able to change the slide at his pace.
Okay.
No, wait.
Just try once more. It's very simple. If you are trying to, share now, stop and share again, and then select screen, and then select your particular presentation. Arijit?
Yes, sir.
Can you take some? Can you try on your own to share and take some screenshot and WhatsApp to Dr. Hemachandran? I think we are seeing now.
Yeah.
Yeah, we see your screen now. Now you open the presentation. Yeah. Make it full screen.
Yeah, it's fine.
Perfect.
It is fine. Now it is coming.
But we don't hear him.
He's mute. He can unmute. So
Please unmute yourself.
Hello.
Yeah, he's muted, I guess.
yeah, okay now.
Hemachandran, please unmute your mic. Now the slides are visible as it is in
Proper shape.
hello.
Are you able to listen?
Now it is okay. Your slides are okay. You can start from slide 1.
Yeah. Okay.
With your introduction, you can start.
Yeah.
It is coming nicely.
Okay.
You are audible also.
We don't see you. You can turn on your video also.
Your video can be turned on.
Oh, okay. Because control changed to some other place. That's a point. Now, are you able to listen? See me?
Yes, sir. Please go ahead, sir.
Oh, okay. Yeah. Good evening to all once again. I thank Anasura and Dr. Aprin for a very elaborate introduction as well as showering nice words on me. I thank the organizers for giving me an opportunity to interact with the IEEE Microwave and Antenna Society members. And I consider it's an honor to be one among the L4 lecture members. And IEEE Society provide an access to current information to all the fellow professionals, and society in the true spirit share the information on online as well as through lecture series. And I congratulate the organizers in effort to take effort taken on this pandemic period to get on the online and share as much as information possible to all fellow professionals. And the topic of today's discussion is on global navigation satellite technology. Nowadays, it's an ubiquitous technology, and once it was a closely guarded technology for military use. Now, beyond doubt, one can say that it's a common man technology. Every mobile application is linked to the current location for one or other reason. Sometimes I do wonder why my health watch need my location information to start the program. And okay, after all, some business may be going under behind the scene, which I may not be knowing why my position is so important. So the use of this technology is totally left to the designers as well as the users. And my talk is mainly on the technology evolution and R&D opportunities for young engineers. The topic is very broad, and I only highlight the various technology happened during the evolution. And most of the time I'll be talking to the screen. It's a bit of caution because I don't know whether I may go offline. So please respond when any query is posed. So with these few words, shall we start? I need some feedback, so I will keep this querying.
Go ahead.
Okay.
Arjit, you follow it up.
Okay. Otherwise, no, I may not be knowing whether link got disconnected or not.
Sure, sir.
Okay. Yeah. Just wait. Yeah, I will be covering basics of GNSS and few introduction to our IRNSS system. Then some receiver part and typical GNSS spectrum in total and the future trend. This is my topic of discussion. I take this particular topic as a learning opportunity in a multidisciplinary area. One can learn RF and atomic clocks, communication and signal processing, geodesy, embedded systems, orbital dynamics, all those things together you can learn by studying this topic. That is the beauty of this topic. I mean, those who want to enjoy everything in one shot, this is an area. In fact, after the World War II, if you look at what happened is October 4th, 1957, Russia launched the first satellite Sputnik into orbit. And the Americans were observing the satellite tone signal, and they were able to predict the arrival of satellite from the tone. That was the context of this discussion, what's going between the mathematician Bill Gur and physicist George Feynman explained the Doppler tracking of Sputnik to APL's research director, McClure. And typically the McClure know the navigation challenges, and he said, well, if you can find out where the satellite is, you ought to be able to turn the problem upside down and find where you are. It's a discussion on March 1958. Probably in the history, it is recorded as the first comments on use of satellite for navigation purpose. And you can see this on the GPS World, I think 2010 May article, the details of the history of GPS. And if you look at the history, there are many more radio navigation systems earlier too. In 1960, LORAN was there. That is a long-range navigation system, which uses typically toned signals. Then thereafter came, okay, for every product on American side, you can see a product on Russian side. Chake is the similar long-range navigation system. These are all tone-based systems, and the position accuracy is of the order of 2 meters and all. It covers nearly 3,000 kilometers using the ground transmitters. And Omega is also another type of radio navigation. All are ground-based. The first satellite-based navigation was attempted by Navy and APL, Applied Physical Research Laboratory. That's called Transit. And few technology developed later useful for the GPS. The Timation is another 2 satellites again developed by Naval Research Laboratory, where they used the first atomic clock. And then only they understood that many places, many other type of navigation system developments are going on. Then US government constitute a form body under US Air Force. It's called a Project 621B in 1972, and took key decisions on what way the system to be formulated and what are the key things to be looked at. There they finalized and spread spectrum technology using CDMA for signal, as well as atomic clock as the two key elements for the system development. And the first project director is none other than Colonel Bradford Parkinson. He got IEEE Medal of Honor in 2018, and it constitutes nearly started with only 18 satellites. Now it is defined with 24 satellites, which are located in 22,200 kilometers above Earth, and nearly 4 satellites per orbit, and there are 6 orbit, and orbits are inclined around 55 degree with respect to equator. That's the way the first set of constellation is defined. To get a visibility of the order of 6 to 8 satellites all the time. You can see the mission statement that time itself. Anytime, anywhere, all weather conditions. Nav data must be available. That is position, velocity, and timing. And initially, it was named as NavStar. That's a navigation satellite for timing and range. Later, everybody synonymously called as GPS because it's a global positioning system. And the first satellite was launched in 1978, and more than 24 satellites by the time they launched. And so many other old satellites rid off because life is only 4 to 5 years initially. And it is declared operational in 1995. Say the key technologies, as I told, we need a stable platform in a predictable orbit. So the space, satellite position must be predictable all the time. So that technology has to be developed. Then ultra stable clock, different types of atomic clocks was one of the key element. Then spread spectrum technology. Those technologies.
मेल एक्स्ट्रा कैप्सूल यूज करने के बाद अपनी फीमेल पार्टनर को आप सेक्स में फुली सेटिस्फाई कर पाएंगे.
Hello. No.
Other participants are requested to please mute.
Then the microelectronics and embedded technology is another key area which could minimize the satellite size. You can see the first GPS receiver brochure with a military person, army person carrying on shoulders. It was around 20 to 25 kg, I think 25 kg that time. Now the technology has evolved because thanks to the Moore law and ASIC development, the size is now 15 millimeter by 70 millimeter. You will get a GPS receiver compared to 40 years back. You can here I gave the reference. The GPS World May and June give the history of all what is happening between the US Navy as well as Army, then Air Force, in arriving at various configuration discussions and options. I'm not going to further on the details. Then some few basics of our school days. Actually, we were using triangulation to find the distant object by measuring the orientation from two known locations. These are the typical geometrical problems we solved during our school days. And actually, that is called triangulation because we use the orientation and position to find the, say here, the landmark, how far away from the baseline. So this was a typical geometrical problem we encountered during using 2D methods. Now, if you go to 3D, the same principle is extended. There are 3 known sources are there. That is nothing but the satellite. And we can measure somehow the radial distance from the satellite to the receiver. Then nothing other than this Euclidean equation we can solve and find out the unknown x, y, and z. Here x1, x2, y2 belongs to each satellite exact position in XY coordinate, some coordinate form that we will discuss later. So we have to find out the range. I mean, R1, R2, R3 is our objective. And typically here we measure as transit time of the radio signal from satellite to receiver is our time mark, that is T1, T2, T3. So once we get T1, T2, T3, we can multiply by velocity of light and get the range. So this type of measurement is called trilateration, because arriving at the position by finding the range. Earlier it was through the orientation, is angle of arrival. This is a time of arrival. This is a difference. Then any measurement you take, there is a range uncertainty, because we are because of the radio measurement over a long distance, we will not be able to get precisely the whatever intersection earlier I showed. So this range uncertainty will always give some kind of uncertainty in your position measurement. So that means you are not able to measure with the simple range measurement, and the range also is called pseudo range. I tell you why it is pseudo range. And because you see, I forgot to tell that when you are trying to measure the time, we are referring with respect to your local clock. The local clock is not as good as an atomic clock used in the satellite. So definitely that is not a choice to carry an atomic clock. Somehow we have to find the clock bias or something. What is the error in the receiver? So earlier problem, we have to solve only 3 unknowns, that is x1, x2, x1, y1, z1 to get my position. Now I have to solve my time also. So that need 4 equations. That means I have to get one more measurement from a fourth satellite. So you can measure the receiver clock bias. That's delta T I showed here. So minimum 4 satellites are required to solve the typical Euclidean equation for a GPS kind of satellite systems. So that receiver clock uncertainty is solved. So this is the modified range equation. This is the only main equation used to solve the position, or similar equations can be derived for velocity also by measuring the Doppler. Doppler is nothing but a direct measurement of the velocity that we will see later. Then to look at the whole entire GPS system, we can see in terms of 3 major segments. One is called space segment, and the other is ground segment, then user segment. The space segment comprises of all the satellites and its signal architecture, all those things fall under the space. Control segment look at the main control centers and the ground antennas to monitor the satellite health as well as for messaging the navigation data. User segment various kind of applications of GPS receiver for users. So entire gamut of receivers fall under the user segment. Bit more on the control segment. If you look at the control segment, again, 3 types of control segments are the control entities are there in that control segment. One is the master control center, which is located at Colorado Springs Air Force Base. Then the secondary station is Vandenberg, California. And there are set of ground antennas. You can see most of them are along the equator to get horizon to horizon view for all the satellites. And this is a typical picture of the ground antenna located at Hawaii. Then there are set of monitoring stations along with the ground antennas. That's blue is Air Force monitoring station, which collect the data from the GPS satellites and look at the health of the satellite as well as the ground antenna is used to upload some of the navigation data, which I will be dwelling later. So these are the typical functionality of the control center. And the space segment I earlier told it comprises of 24 satellites. And presently there are 4 variants of the satellites are on orbit. You can see the first block 2A and block 2R is the legacy satellites, I mean with the old signal structures. And now it is modified. That also I'll tell later. You can see the old legacy, only 7 satellites are there. All others are modernized satellites. It is named after block 2R and block F, block 2F and or GPS 3. These are all the naming convention. You can see the lifespan of the satellite increase from 7 years to 12 years, now 15 years. And the size also changed. And for ranging, they use, I said the precise orbit determination of the satellites is one of the key necessity. And the new generation satellites are equipped with laser retroreflectors. So we can precisely measure less than a centimeter accuracy using laser reflectometer for new generation satellites. And earlier type of satellites, they use CDMA ranging through another signal. Typically, it's called satire modems using long interferometry base, and again, you will be getting orbital accuracy less than a centimeter kind of accuracy is possible. This is the total space segment. Then when you look at the signals, there are major, the legacy systems has L1 frequency as well as L2 frequency. That's somewhere around 1575.42 is the L1 frequency, and L2 is 1227.6 megahertz. Both are multiples of base frequency, atomic clock frequency, that is 10.23 megahertz is the atomic clock. It is maintained on orbit. And typically there is a code called codes acquisition code, which is used for all civilian use, and P code, which is used for military use, and CA code, that's a codes acquisition code, is short duration code of 1 millisecond long, and nearly 1023 bits are there, and it is clocked at 1 megahertz. So typically the duration is 1 millisecond duration. And the similar code, if you look at in the P code, it is clocked at 10.23 megahertz, and the code duration is very, very long, 266 days long code, but it is sliced into set of week long code, I mean 1 week long code, and that code will are distributed to various satellites at random, and every week also they change at the Saturday to Sunday midnight. So this long code is very difficult to track for any civilian purpose, and that's the way the US military is protecting the P code. And in fact, more than that, it's an encrypted. And you can see that the P code is available both on L1 and L2. This is the legacy structure. And later from 2005 onwards, L5 was introduced. And that's a new signal. Again, it's a multiple of basic 10.23. It's in 1176 megahertz. And there are 2 more signals which is of military nature. That's L3 and L4. It's not disclosed much. Then if you look at the modulation, just for the academic purpose, I am telling that carrier signal is 1575 megahertz, and if you take the wavelength, it will be around 19 centimeters. And CDMA needs that PRN coding required. That I will come back later. That is a code I am referring here. The code is clocked at 1.023 megahertz, and 1 microsecond code length is around 300 meters. That means even we are able to identify one pulse correctly, we will not be on dot because we are 300 meters away. And the actual signal is nothing but the data. It is called a navigation signal, which is sent at 50 hertz. And this 50 hertz is the real data to be transmitted to indicate the time at which the particular signal is sent from the satellite. So this 50 hertz signal is spread using the PRN code. So it's called CDMA, code division multiple access. And these exclusive are the data of code and data, navigation data is broadcast through carrier on a BPSK modulation. That's the equation at the bottom side. And similarly, the P code also modulated in this form. All signals are summed at the transmitter side and sent. And okay, this is a typical spectrum. You can see that the CA code is a very small spectrum because of 1 megahertz is the coding frequency, clocking frequency, and P code is 10.23 megahertz. So it's broad, and 20 megahertz is the spectral length. So when your receiver design, you have to take care of all these factors. I mean, it must be able to accommodate the broad band for the P code reception and very shorter bandwidth for the CA code reception. Again, for a academic interest, this particular code, even though it looks very cumbersome, it can be easily generated through this particular 2 shift registers, and with I think on the you can refresh your coding theory here. Those are all reducible polynomials, G1 and G2, and using that you can get a full length code with 1.023 clocking, because 10 bit generate 23 bits, 10 bit shift register. So the entire clock sequence will complete within 1 millisecond. So here the G2 is the one identify the satellite. Every satellite will have a unique G2 combination. So the satellite can be identified with respect to that. And this will generate a code which is called Gold code, named after the Robert Gold. And that's why I said you can refresh your coding theories once again here. And every 1023 epoch base frequency 10.23 megahertz epoch is used to control this. At the end of the code sequence, it will be this shift register will be reset and start once again. So the precise timing is maintained with respect to atomic clock. Then I talked about satellite position, and satellite position is indicated on a coarse way by Keplerian parameters. Typically, the Keplerian parameters are 6 Keplerian parameters are there: inclination, right ascension, and argument of perigee and true anomaly, and the mean argument of perigee, then mean anomaly. With that 6 parameter, you will be able to identify the satellite on a typical Earth, around the Earth orbit. It's called Keplerian orbit in the sense it's a 2-body problem to represent the moving body around the Earth. Actually, this is not a precise orbit, and it will be around 1 to 2 kilometer disturbance will be there, depending on whether it's a low Earth orbit or a medium Earth orbit or a geo orbit. Typically, the least disturbing orbit is somewhere around where GPS satellites are located. If it is closer to Earth, the orbital disturbance of the order of 5 to 7 kilometer will be there with the Keplerian orbit itself. So this is typically called oscillating orbit. I mean, defined. Orbit without a dispersion is called oscillating orbit, and for that 6 parameters are required to, and you can see the what is inclination, what is the omega. Omega is the right ascension of the ascending node. I mean, from the Greenwich Mean Time, at what point it goes above the equator, and the angle is called the right ascension. It is defined with respect to vernal equinox. This is the way because we have to define the satellite over a long duration. So they taken the inertial frame to define. That's why the vernal equinox is coming into picture. Then, as we all know, that satellite orbit experience a lot of disturbance, typically by atmospheric drag, thermal forcing, then other planetary interference, then relativistic effects, then Earth gravity variation, solar radiation pressure. All those things will have a lot of disturbing force on the satellites. That means whatever Keplerian orbit we said is not that accurate to have navigational purpose, but that is good for initial acquisition of the satellite signal. So GPS has defined an ephemeris. Ephemeris is a more accurate definition of the satellite orbit, where they included a set of sine and cosine terms for latitude variation, then radial oscillation, as well as inclination difference. Then there is a mean anomaly was introduced. Then there is another parameter called time tagged data. That means the data is time tagged for 2 hours. Thereafter, the validity of the data is not that good. So that way, we are providing a very precise orbit information over a defined duration. You can see the orbital disturbance over the Keplerian orbit. This blue is the Keplerian orbit, and over that slightly, even though it's a slightly exaggerated, this kind of oscillation is always there on the orbit. So here one can even study the orbital dynamics is to get modeling of the satellite orbit, because actually this is not the GPS receiver alone. If you want to study and maintain the satellite on orbit, you have to precisely monitor the range signals and modify the ephemeris periodically and give the best estimate to the customers. So that means the orbital study for each orbit definition, it's different. I mean, one cannot copy one model to other. Yeah, for instance, GLONASS use a different methodology. They are not using the Keplerian orbit. They are using ECEF coordinate frame with velocity as another input. That I'll come later. For your information, this GLONASS use a different methodology for representing the precise ephemeris. And okay, even though I earlier told about the clock error, now the clock error is not the only error. Actually, there are many error encountered from the satellite to receiver, and you can the first entity we talked about ephemeral errors, and which we seen how the errors are there and how to model. All these modeling parameters are there part of our navigation data. You can get the data and correct the orbital information of the satellite, and those information also they are part of the interface control document. So if you look at the typically a satellite error contribute around plus or minus 2 meters That means of the order of again 4-meter error can come if you are not properly updating the ephemeris. Then clock error is there, that anyway I will deal later. Then multipath error is nothing but signal may be reflecting from nearby tall structures or then big mountains. So that will give a different path length. Path length will not be able to properly estimate. System noise is there, antenna phase center error is there. Then ionosphere and troposphere, which are the major errors. Ionosphere error is because of the dispersive medium of the ionosphere where electron content is there. So there is a concept called group velocity as well as phase velocity. The carrier experience the phase velocity, and the navigation data and the code experience the group velocity. The group velocity will slow down and the carrier will advance. So in the range measurement, this has to be properly accounted. That's why in the bottom equation, actually this is the range actual range, and the receiver clock bias you have to adjust from the 4 satellite information. Then satellite ephemery error, ionosphere delay error, troposphere error, then multipath error, and like that. All these errors, when you cancelled from the actual measured pseudo range, that's a row, then you will get you can find out the actual range. That is the way you have to come down to the actual range from the pseudo range what we measure. And the troposphere error is another type of error which because of the troposphere we consider something from below the 50 kilometer. Even though troposphere is only up to 20 kilometer, we take the stratosphere also into account, and say lumped models are available. And typically this is because of the refraction of the signal at the interface, because of the density as well as moisture content. And these are all the typical free space to atmosphere entry point refractions. This also will introduce path delay. There are models to correct the troposphere error, but ionosphere error, because of the dispersive medium, suppose you have 2 frequencies, you can correct. There are some equations to find the total ionic content and electron content. I mean TC, say total electronic content, and correct using dual frequency measurement. But these errors are to be quantified in a receiver. So that's a challenge in the receiver design. And typically this is indicated as user equipment range error. And here one part is related to satellite systems and atmosphere. So it's called user range error, and remaining part is called user equipment error. And typically RSS is used to quantify the receiver performance. And another error which I not highlighted earlier, it's called here fourth error is a geometric effect. That means when the satellites are too close by during our observation, because sometimes it falls like that. Some satellite may be obstructed by a tall building, and that time you will be getting a narrow angle view of the whole satellite. Then we will not be able to get the proper measurement on the other 2 axes. So that, or rather I can say that your measurements are weak, so there is a dilution of precision. So this dilution of precision is called a geometric dilution of precision. So whatever URE you are getting, earlier I said all those things, that dilution of precision will be amplified by this URE will be amplified by DOP, that is a geometric dilution of precision. So that will be our net position accuracy. When you get at the receiver side, we have to consider DOP also. So when the satellites are wide apart, we have a good DOP, and we will get very good position accuracy. And at the same time, when we are tracking a low elevation satellites, the signals are supposed to travel through a long atmospheric medium. So those also introduce more unexpected ionosphere and troposphere error. So generally it is better to avoid those satellites. We generally use the elevation mask. I mean, don't track satellites below 5 degree or 10 degree. And there are special designed antennas are there which will automatically or which will reject the ground clutters. Those areas also one can look at it. Then, yeah, coming back to the actual data, which is navigational data. Navigational data, this is the key data which is transmitted in the form of subframes and frames. Okay, there are subframes 1 to 5 because there are some data which need frequent update. So the subframe 1, 2, 3 are the frequently used data for position information. Each subframe contained nearly 10 words, and each word is 30-bit long, and that means around 300 bits are there. It takes nearly 6 seconds to transmit one subframe. Like that, 5 subframes are required to start with the position, interpret the navigation data. So typically it takes around 30 seconds. You can see the vertical axis and 30 seconds to get all the frames. Then only you can start your navigation program. So every frame start with the TLM. TLM is our code, known code one can use for tracking or detection of the arrival of signal. So this preamble is known, so you can use your receiver to tune to that and identify the start of the frame. And how is nothing but the handover word. That is nothing but the time mark of the signal transmission at the satellite side. At what time mark this particular signal started from the satellite. So the how is indicated by some 17-bit seconds over a week. So GPS time is compared to any other time, it's a continuously counting time. So continuously counting means it's starting from its inception onwards. I think 8th June 1980 is date of birth as far as the time mark is concerned. At the midnight, from Saturday to Sunday midnight, it's clocked 0 in 1990. From where onwards, it is keep taking every second with better than 10 nanosecond accuracy, and it will be corrected by other ground systems. So every and so this continuously incrementing time is the GPS time. So it is represented as seconds passed over the week is one information, and number of weeks as another information. So number of weeks is generally represented with 10-bit. So generally it overflow after 19 years. So after 1980, 2 times it's overflown and it is resetted and restarted. So that has to be accounted in the receiver. And all the data is protected by Hamming code in the legacy systems. The code is 32 or 26 is the Hamming code formation. That's a parity code. And okay, the 4th and 5th frame occupy various other health parameters, UTC, as well as the almanac information. Almanac information is nothing but the earlier 6-parameter model of all the satellite will be sent one by one, and over 12 minutes and 30 seconds, all the 24 satellites information will be available through subframe 4 and 5. So that's a less periodic data, and that is a way it is architected. So that's why I said it's a subframe and frame concept, where handling the needed fast varying data as well as other slow varying data simultaneously. So this 12 minutes data, you can call it as a super frame. And okay, any satellite system need one type of coordinate definition. And typically here we are using Earth-centered Earth-fixed coordinate system. And the coordinate system is an approximation of the Earth as a ellipsoid. So the Greenwich meridian and equatorial plane intersection point form the x-axis, and along the pole is z-axis, north pole. Then y-axis is 90 degree on the right-handed system. That's the way it is defined. Since it is x-axis is fixed along the Greenwich meridian, the frame rotate along with the Earth. So that's why Earth-centered Earth-fixed frame. And this is an ellipsoid, so it needs a few parameters to define. Typically, the gravity and the semi-major axis of flatness, all those things are part of WGS 84. Here, the data and definition, so many things are there. That's why here the part of the geodesy we can study and how to represent more accurately. In fact, this is not the system followed by Europeans. They use the International Terrestrial Reference System, and GLONASS use another reference system called PZ90. Earlier it was PZ80. Now, like WGS 84. Earlier some other number was there, and I don't remember. But anyway, every system use a different frame of reference. But at the same time, there are algorithmically one can transform one coordinate frame to another, because all are approximation of the ellipsoid in one form or other. An ellipsoid needs what I said, the semi-major axis and flattening, then gravity, all those things. So that's a way the coordinate systems are defined for GPS. Then another error, actually this is intentionally generated by US military. It's called selective availability. The name looks funny, but it's nothing other than a clock will be intentionally deterred. So normal users will not get to the position better than 100-meter accuracy. Will be keep oscillating between your position. So this was a major nuisance even for the military in those days. I think during the Gulf War, 1991, short duration of time, they removed the selective availability because for the usage of a commercial receiver for military purpose. I think 1 year they removed, as history says that. Then by 2nd May 2000, totally the selective availability is stopped by presidential declaration. Honorable President Clinton was there at that time. He only declared the stopping of clock dithering. Probably these are the hidden techniques every country trying to populate their own navigation system, because at any time it can be enabled and you may not be able to get it. But I think now it will be very remote, because they are using better signals for other military purpose. So now anyway, after this GPS become more common to common man. Say next segment is the user segment. User segment generally defined in terms of standard positioning system for normal usage, and precise positioning system for military application. And typically it's a collection of receivers of different class. I mean, for survey purpose, some sporting, then say recently mobile application, then aircraft, ship, tank. So many things use the receiver with various capability. So all this fall under the user segment. In fact, this is after 2000 only major usage started. Then another technology is the clock technology, and we are looking of an atomic clock of stability 10 raised to minus 12 to minus 13. This 10 raised to minus 13 is possible only with cesium type of clocks, which is very bulky and presently nobody is using, because anyway you can correct the onboard clock to algorithmically, not tinkering with the physics package. So rubidium clocks are used mainly, and which is much cheaper. Today even rubidium clocks, this is around 20 kg cesium clock. Presently even chip form it is available. And the research is on the another hydrogen maser clock is 10⁻⁻15. Those are the clocks generally used for ground system maintenance. Then optical clock is still on R&D, 10⁻⁻17. These are all use the quantum technology. Quantum entrapment technology is used for optical clocks. Then if you look at the cost of the receiver, there are civil receivers $10 to $200 available, but receiver for survey is very costly, $2,000 to $5,000. Then there are DGPS receivers, differential correction receivers with precise carrier phase. Those things I will deal later. So those are still costly. And the reference station receivers, what we are using is somewhere around 1.2 crore worth reference receivers used in the monitoring stations. Then another set of receivers are called military and space grade receivers, which is very difficult to get from abroad, because it is regulated to ITAR, that's International Treaty on Arms Regulations. And any receiver having capability to detect more than 512 meters per second or altitude 30,000 feet or typically 10 kilometers or 2G acceleration is restricted. I mean, you are not supposed to sell across the country. So here a lot of research opportunities are there. Presently in India, only one company is making, that's Accord Systems. And for all other our ISRO in-house use, various centers have their own capability, and they have demonstrated for launch vehicle as well as the satellite. Then typically, if you look at the spec of the receiver, you can again classify as commercial, industrial, and mill and space. That's another type of receivers. Then capability, number of channels, and the constellation, number of channels. Simultaneously, how many satellites can be tracked and used. Then constellation, whether it's different GPS, GLONASS Russian system or other systems are able to track. Then the accuracy of position, velocity, and time. Then acquisition time. I mean, after the power up, but how fast you are able to give the first position fix. That's a time to first fix. And what rate you are able to update the position. That's whether 1 Hertz, 5 Hertz, 10 Hertz, like that. Then what's the type of receiver data available, whether it's full data or this NME. I mean, NME is two formats which I will deal later. Those are the format on which serial data is available. Then whether anti-jamming capability for the receiver. Anti-spoofing means some pseudo satellites will be giving the information and try to steal your position location. That's called spoofing, just like the word used by web technology. That's spoofing. Then the multipath detection and mitigation capability. Then robustness to perform in water, higher dynamics and vibration, and integrity reporting, whether the receiver position or velocity information is believable, or whether it can generate some alert. If I'm not okay, whether I'm able to alert you. Those are the type of capability of the integrity reports. Then coming to typical block diagram. Even though this is a very primitive block diagram in the sense it only says that what are the blocks involved in the receiver design, because you have seen the cost of the receiver from $10 to 1 crore type of thing. So that means the complexity of the design also and capability also changes. Traditionally, we use this kind of architecture. I mean, there is an RF front end which convert the L1 signal to a baseband, and some ADC, high-speed ADC is there to convert to binary, and it will be available on the baseband somewhere around 4 megahertz to 20 megahertz or even 70 megahertz depending on the design. Then there is an acquisition phase as well as the tracking phase. There are different types of correlators people use to acquire the data. I mean, you are matching the incoming signal with locally generated PRN sequence. And when you are able to get a good match, then it will be transferred to tracking, where the signals be closely tracked up to the phase level. Then you will be able to decode the navigation signals. Typically, a microprocessor is used to take out all the navigation data, then compute the pseudo range, then compute our Euclidean equation and find out the position, velocity, and time, and typically message to various users. This is the typical architecture. Some people use the SDR, I mean software defined radios nowadays. It's a totally software architecture except the very small RF front end. So that's one kind of architecture, or otherwise you can use some part hardware is the FPGA based system on the control software and hardware. It's a typical challenge on the co-design of hardware and software. Here that depending on the complexity, the cost as well as the challenges are many. Actually, this is a typical mimicking of correlation. You can see the incoming signal is matched with locally generated pseudocode. You can see sometime it peaks. That's a actual phase of the signal match with the incoming signal. So that time you have to time tag and use these two time difference, incoming satellite PRN code generation time as well as the satellite arrival time is used to compute the time difference. So if you, this is in the digital simulated data, but actual real raw data look like this, because satellite data when it is received at the receiver front end, it will be around minus 130 dBm. That is well below the noise floor. Noise floor is for RF noise floor is minus 130 dBm. No, 110 dBm. So nearly 20 dB down with respect to noise floor, but various correlation and correlation properties of the code, you will be able to acquire the data. And since that satellite is in motion, the carrier frequency also will be changed because of the Doppler. So you have to search for the carrier shift as well as the code phase. I mean, code also, we don't know at what phase it started. So you have to search for the entire code phase as well as the carrier Doppler. So simultaneously, you have to search both carrier phase as well as code phase. And code searching, generally we use DLL, that's a delay lock loop, and or you can go to frequency domain approaches using FFTs. Typically in the frequency domain, correlation can be defined as, no, typically the convolution is nothing but multiplication of two frequency domain inputs of the incoming as well as locally generated data. But if once you take to the conjugate of the data and multiply, then it's nothing but a circular correlation. So that property can be used to simultaneously search the frequency as well as code much easier. So that means you have many options like serial search, parallel search, then FFT based search algorithm. So here are a lot of opportunities are there to explore. Then typically carrier needs COSA loops for phase synchronization. So there also the concept of discriminants, I mean discriminating functions of whether coherent or non-coherent. You can define and experiment with different discriminator and get what is a capability under different signal condition, like accelerating condition or higher velocity condition. What will be the type of discriminating function to be used in a typical scenario? So after tracking, you will end up in typically a sequence of nice square waves if the phase tracking is over. So here onwards, you can assemble all the bit patterns of 1200 bits of navigation data over 30 seconds, then decode the frame as per the frame defined earlier. So that means you are having all the ephemeris of the satellites to identify the satellite, as well as you have the range because the time of the week is known and the week number is there. Then you can calculate the transit time of the signal. I mean, range is there, your satellite position is there. Now you can calculate. Typically, you take a software architecture. It's a challenge once again for a embedded system designer, whether to go for an RTOS based system or an ISR based system, where you can have apportioning your software modules. I mean, which satellite to be allocated for tracking, for satellite allocation module, satellite data decoding module, then output various format you can output, taking the measurement from the hardware. So then computing the navigation solution. Suppose you have multiple architecture, you need multiple solutions and how to mix the solutions. So many very extensive compute oriented system where you have to watch the signal in 0.5 millisecond, that means 500 microseconds. You have to look at the all the tracking handles, I mean correlators, whether it is full or getting ready for signals. So at least every 0.5 second millisecond, 0.5 microseconds you have to look at it. Sorry, 500 microseconds you have to look at, because it's half the duration. So sorry. So that's the way. Then when you look at the receiver output, this receiver output give 1 PPS accurate pulse with atomic clock stability, because it is synchronized with the satellite clock. So you are almost getting stability of the order of atomic clock. Typically, we say around 30 nanoseconds to 15 nanosecond stability of this 1 PPS. I mean, 1 pulse per second clock will be generated by the receiver. Then output of various data formats are available. That's called ASCII data are there, binary format. Some of the company keep the proprietary data. They will not disclose. Instead of that, they release the data in NME format, that is National Maritime Electronics Association. There is a data format available. Then RINEX format is nothing but receiver independent exchange format, which is generally used for research purpose. So any receiver, you can collect the data and compare if the data are represented in RINEX format. Then there are some other format SC104 that I will talk later. So this is a typical overview of all the receiver and receiver output. Then I am not complete if I am not mentioning anything on our IRNSS system, because this is exclusively developed for our Indian region. So it is called Indian Regional Navigation Satellite System, and we populate this satellite with geo configuration. I mean, all 7 satellites are in geo, and 4 of them are geosynchronous. That means all are inclined at 29 degree. So those are the one form figure of 8 pattern with respect to the ground trace. So all the satellite will give a very good coverage over India and around. I mean, West Asia to East Asia, full coverage is there. Satellites are kept at 32° longitude to 131° longitude. So we also put a mission statement for standard positioning less than 20 meter, and our military service is called restricted service, and it's called 10 meter, less than 10 meter accuracy is there. So this constellation, we use the different types of data, signaling signals, and we are using L5 signals because at that time that US government or other government agency, intergovernmental agency was not sharing L5 for us. So we resort to L5. L1 was not shared. So we use a L5 band for our BPSK signal. And S also we are sending S band signal also used. And in both the S band and L band, we have both BPSK as well as restricted service. For restricted service, we use a modern signal called BOC model, that binary offset coding. That means here we are using another subcarrier to modulate the main pseudo-random sequence. So the advantage is the main spectrum also split with respect to carrier. That means signal interference will be less, as well as spectrum can be reused effectively. And we have only 25 hertz navigation data. Since we are using half rate encoding, FEC encoding, the data rate is 50 samples per second. So we are all sending with all these are all modern signal structure what GPS system employ, and our BPSK code length is 1 millisecond, and total bit is around 292 bit over the frame. I think next is the frame definition. We are here we are using subframe of nearly 300. Sorry, subframe here we have only 4 subframes, and first 2 are fixed frames, and the next 2 are variable frames, like we can use for various other purpose other than navigation. Here we are using for many other services like disaster management, then potential phishing zone indication. All those variable messaging frame is used. So we are using only 4 subframes, but the period is almost same because of the half rate encoding. And this is all about our IRNSS, because the paucity of time already running late, I think. So now a few insight on how to improve the accuracy of our standard GPS system. For that, there are differential GPS systems are available. That means which can there will be a master station which receive the satellite signals and precisely find out the errors, and either indicate to the local rover station in the ground-based system, or through a space-based system that's called S-bus. We send the S-bus signal uplink to a geo satellite, and those satellite will send the correction signal down. And if you look at the globally here, India has already populated 3 S-bus signal, which is called Gagan. And you can see from Europe, IGNOS is there for Europe, SDCM for Russian, then MSAS for Japan, and wide area augmentation system for US, and some another Canadian augmentation system also there. That means over the equator, many augmentation systems are there to improve the GPS data accuracy. So all these augmentation system estimate the GPS signal accuracy at the ground through set of ground monitoring systems and uplink to respective satellite in their own region. So this is one way you can improve. Typically, the improvement is 10 to 15 meter position inaccuracy can be reduced to less than 5 to 3 meters with S-bus augmentation system. Then another effort undertaken by GPS is modernization of their GPS. You can see the first is the present signal which I so far I dealt with. Then new signals are introduced called civil signals. That's called L1C and L2C. I mean commercial signal. Those are using the modern signal structure like BOC as well as alternate BOC, time division multiplex, the TM BOC, then mode, what you call M mode signal, that's a military signal. You can see that here what I said about the spectrum got split because of the BOC modulation. The green signals are M signals which they used along with the L5 signal. The L5 signal they during the modernized satellite architecture, I think block 2F onwards modernized signals are available. There this BOC modulation is introduced and to another green are the spectrum got splitted due to BOC modulation. Actually, this was discovered by Dr. John Benz and I think in 2001, and thereon was it was used by all the constellations for effective utilization of the spectrum. And towards the end, I can say that this is the total GNSS spectrum. If you look at, there are many signals are in space from GPS and Russians are using. I forgot to tell that frequency division multiplex is used by Russians in the earlier GLONASS. Presently, they are also switched to CDMA. Then from European Space Agency, another set of signals are available. That's called Galileo and Galileo constellation E5 to E1. Then Compass is another constellation from China. They use B1 to B6. Like that, so many signals. And Japanese are having QZSS. That also use the same L1 as well as L5. Then, of course, our Indian system, IRNSS. Oh, yeah, I forgot to tell, Indian system is later named after NAVIC. That's navigation with the Indian constellation. Our Honorable Prime Minister Narendra Modi declared in 2015 after populating all the satellites. Then Starlink's also future going to play with another set of navigate signal that I heard in one of the seminars. That means nearly 75 signals are in space at a time from various constellations, and receiver design is a real complex thing, and one can learn a lot by exercising the design options and making a robust and as well as more precise receivers. Then typically, if you look at the advantages, I think most of you all know that ease of navigation, any small chip can give you the navigation information with a very good accuracy. It's both civil and military use. Geographic information system is one thing. Everything is time tagged. Is compared to any other navigation system, is economic, easy, shortest, and fastest to get the solution. Many location-based services are there, and host of application on science, agriculture, airline. Then personal navigation is the one which is more prominent nowadays. Typically look at the disadvantages, inaccuracy, and then external interference, tall buildings and canyons is a challenge all the time. And the cost of maintaining the satellite is another area. Then multiple constellation need interoperability and compatibility. Okay, these are all the things they take at the design side and intergovernmental coordination. Then detect and mitigate the harmful interference. That's one area we have to more careful with. This can happen with even land-based interferences. So I am making an open challenge to your antenna, IEEE micro and antenna community. This multi-channel controlled reception pattern antenna is one challenge. That is our most of the receivers use the patch antenna or choke ring antenna, which is almost an omnidirectional with respect to ground, and we are forced to listen to all signals from all sides. So there only this jamming is coming into picture or spoofing and all. So suppose I can identify the interferent signal orientation, I can design the change the antenna pattern using controlled reception, and this is a real challenge for antenna as well as micro designers, how to arrive a patch antenna configuration of small form factor for interference mitigation. So this is an open challenge to you all. Okay, then if you look at the future trend, it's a high volume business. You can see in US in $1 billion are coming, and as well as even civil and defense use is increasing day by day. That's a future trend. Okay, plenty of applications in the research field. Typically, I said towards the end, you can see the antenna can be used for finding the orientation, then smart application, aerospace and mobile application, lidar application, space weather, soil science, geodata. So many are there on the research area. So with that, I am winding up. Thank you for the kind attention and questions, please.
Thank you, sir.
Took a long time. Sorry.
Hemachandran, thanks a lot. In between some I have a message. We have some distinguished guests are participating. I request Dr. Surendra Pal, Dr. Sudhar Rao, Dr. DC Pandey come on the screen because that will be a great motivation to our young scientists or professionals and students. Over to Arjit.
Yeah, thank you, sir, for such a nice session, a complete overview of GNSS system, starting from the global scenario, the different technologies involved. So maybe now we can take a few questions. The participants can unmute and just ask the questions directly. We'll love to have an interaction. Maybe for a start, I'll ask a question myself. So,
Okay.
sir, okay, we had a very nice overview of the different systems involved. So, why don't you share some of your experiences with working with ISRO? Maybe something related to GNSS only. Maybe the development of GPS that gains the challenges you faced and the methodology and your experiences.
Actually, I started this work somewhere in 2005 as a TDP. I mean, technology demonstration proposal, as in our ISRO parlance, and it was a hard time for us to move to this field because ISU is mainly on the inertial navigation, and our knowledge was very limited in this field. But really, the strength was the design team. I am one among that. Actually, Dr. Mohanlal was there, Harikumar Ganesh, then Radhakrishnan, then now new generation, so many people added to that, Anish, then Vinod. All those people really contribute a lot on the real development of this receiver in the present shape. But real hardship was on design, arriving at the architecture. Because of the our strength in FPGA front, we went with on FPGA based architecture. Later moved with standard microcontroller based architecture, and now our system is more robust with both FPGA as well as microprocessor together. So we can handle all kind of navigation signal. Earlier we were limited to GPS, and actually it took 3 design cycles to mature. And as I said, this is a typical technology denied. So to learn a receiver of high dynamics nature, that means it has to track the signal up to 7 to 8 kilometer per second. We need a very high Doppler has to be tracked. Then high G it has to withstand. Typically our launch environment you say 5 to 6 G. So the entire design is not textbook design, but you can learn a lot from the textbook, and you can experiment with and come to this kind of design by many iterations. Then yeah, and the RF front end, Mr. Karthikeyan helped us earlier. Anyway, it was a collective learning. It's not an individual effort. So many things learned collectively. We had regular meetings, sharing the information, and move ahead along. Yeah, it was a nice experience for 4 to 5 years. Really, we get out of the inertial to radio navigation.
Thank you, sir. So,
in fact, I could learn a lot by interacting with Dr. Paul sir. He is there, I think, online. So I can. He is one of my guru on this field, on fixing the signal strength, understanding the signal strength, and how to make partitioning of RF versus baseband signal. So many things. And another one, Dr. Palsule from SAC, he also taught me a lot. Because every meeting we have very good interaction during the evening hours. So I could learn a lot from him.
thank you, sir. I think Dr. Paul is there online.
Yes, sir. Namaste.
Namaste. Congrats, Hemachandran. I'm really proud of our friendship, and we have been colleagues for long. I had never heard such a beautiful lecture on GNSS. I'm sure the
Thank you, sir.
researchers will get in depth. See, you have gone from very fundamental to the latest thing and how they can proceed. You see, I mean, what he told, we also faced that problem when we wanted to make a satellite positioning system, we call it. Rockets they don't allow, and satellites also they don't allow. So we developed with the help of with the Accord software. I put 5 of my colleagues, led by S.G. Basu. I think Hemachandran knows him also. And we had been in constant interaction when we were designing Gagan and also IRNSS. So now, actually, I mean, like Hemachandran, I'm also a retired person, but we feel very happy when, the ISRO is using Gagan, ISRO is using IRNSS. And recently on 29th April, Gagan was used in, with the help of Gagan, one ATR 72 of Indigo Airlines landed at Kishangarh in Ajmer airport. And I think Southeast Asia, that's the only system which has been used. And Airport Authority of India is the only agency which has used, only Gagan for landing purposes. So Gagan, IRNSS, coupled with all the things which Hemachandran talked about it, you can really get very good accuracies. And I mean, I'm not competent to comment on his all lectures. They're very wonderfully well. He has collected a lot of things, but I wish he could add one thing, that somewhere in wireless, this GPS world, only one document came, one study came,
Correct.
that more than 60 satellites or channels, if we take it, the accuracy does not increase. So he said that we have got something like that, 75 channels and
70
all those
satellites
things.
and all.
Yeah,
Yeah.
so really we should make a receiver which can have a GPS and maybe IRNSS. Now, in view of latest experiences which when we are sharing, persons are sharing in the news as well as on the technical journals, that uh, GPS is getting disturbed over Finland and Sweden, and GLONASS is getting disturbed over Ukraine. And when Iraq war, they increased the accuracy, but some military persons told me, defense persons told me that many times the GPS is being disturbed over Indian region also. So I presume that IRNSS will serve the purpose, that gap in between. And last thing which I want to add, it's a technical thing. For technical thing is added to my friend Hemchandran's
Yeah, sure,
presentation,
sure, sir. You are the master.
that NTS-3, the GPS satellite, new GPS satellite, they are
Yeah.
putting in geosynchronous orbit. And we were
Oh,
the first person, Indian administration or ISRO was the first administration in the world that we have gone to geo orbit. And we also gone to S-band,
yeah.
because, the geo
All
orbit,
other.
because we are a regional system. Now, Americans are going to geo orbit. Even
Yeah.
Russians are also thinking to go to geo orbit. So there's a good scope for doing research. There is a very good scope for doing industrial applications of GNSS, and I'm sure his lecture will encourage everybody. Hemchandran, send me your slides if you can.
Yeah, sure, sure, sir. Definitely I will share.
So I must congratulate you and I must thank you that you have given such a wonderful lecture. That too, you spoke 2 hours without taking a rest. More than 2 hours.
Oh, 2 hours. I don't.
Almost 2 hours. I've been
Oh,
listening from the first moment
oh.
to the last moment.
I
So thank you very much.
okay. Surely I'll share.
Yeah, yeah. My appreciation also for the speaker, Hemachandran, Dr. Hemachandran, and also to Dr. Surendra Paul. He has been a constant support for our chapter, APS and MTTS, and he has appeared as a speaker also several times. But all has been online recently. But we want to soon have a in-person event, and where we want to invite Dr. Paul, Dr. Pandey, and of course our local experts like Dr. Aprin, Dr. Hemachandran, and others are there. So we want to have a good event with all your presence, but one in-person event in Trivandrum. Yeah, Dr. Aprin, you may add please on the plan.
Yeah, surely we are planning mid-June or July or that range. So we will be directly interacting with all these legends and arranging a seminar or the talk section on one day or most probably maximum 2 days in a hotel. So we will be approaching you, sir.
Sure. I think, have a small session on GNSS, and maybe Hemchandran can talk. I'll also talk. He can reduce quite a bit of his thing to maybe 45 minutes or 1 hour. Because 2 hours, everybody start getting bored. And I had an interest, so
No,
that's
no,
why I went
sir.
through every
Actually,
slide.
sir, my idea is to expose the technology, not go in depth. That's why I said so many signals are there. Anyone can pick up. If one is absent, you can go ahead with the another one and
Yeah.
give a very good accuracy.
And I suggest Dr. Saab, in IST we should start a course on GNSS. See, Dr. Mohanlal is there, Hemchandran is there, then I think others are also there. I'm forgetting the name. He had a
Actually,
big.
yes, sir. Yeah, I
Sir,
understand.
last time, last 2 semesters, I took a class
Very good.
on the GNSS alone, but other area in
Full-fledged course on GNSS. And Pratap Misra's
We
book
can
is
have
better
one
than
elective
Garibal's book.
course. we have some module, but we can have a complete elective course maybe.
Yeah, you better have it because a lot of industrial applications are there.
Right.
And buy Pratap Mishra's book, Pratap Mishra and Parange's book, because Garewal book is costly and it does not give that much. It's too much of mathematical.
We'll discuss in length on this, sir. When you come here, we'll discuss. And it has to happen soon. Dr.
Okay.
Raphan, action item on you.
Yeah. Okay, I will take it, sir. So I request Dr. D.C. Pandey to come on the screen, please.
See, I'm sorry, my video is not good at the moment, but I will say that okay, I have learned, heard first time a talk on the GPS of this type. I mean that it is a wonderful talk. What that our Dr. Surenpal told, because I keep on listening to him about the Gagan and other thing. We interact very closely and other thing. But this talk was the really eye opener for all the young people. And the thing is that what Dr. Pal was talking, that okay, I know about the GPS and other system because Accord people used to come for qualifying their system for the EMI EMC. So I used to keep on understanding what is this GPS. But today's talk has really opened a, it is a beautiful. I compliment Dr. Hemachandran for such really a very good talk. Very good talk.
Thank you. So, if anybody further wants to interact or maybe have any questions, they can come. Otherwise, sir's mail
Otherwise,
is
we have to
shared.
submit the assignment.
Otherwise, they can get back later. He has shared his email ID. I think he'll be very glad to answer your queries. In the chat box, any questions?
No question. At least again, I wish to congratulate and appreciate that he has given a wonderful talk.
Really, I think all our students have got inspired by today's talk, and most of them, many of them,
Students are doing some project work in this area, understanding the physics, little bit of mathematics also initially, and then design something. It may be antennas also, or it may be the system, or it may be some components. So Professor Anu, if you are there, try to involve couple of students in the work and request Dr. Hemachandran, Dr. Apren to act as their guide, and I'll also be very happy to involve.
He has already given a topic, develop a multi-band antenna.
Yes.
And I'm adding further, develop the multi-band antenna with good filtering and take care of the multipath by either ring string or maybe, now I saw on paper where around the antenna, they are not putting the grooves. They are putting the printed rings itself. By which one can develop. So, IRNSS action, L1, we have got now L1, L5, new IRNSS will have L1, L5 and S. So our system is more complicated than others.
Yeah, correct.
And then we use Bach modulation. And Bach book gives the Bach modulation. So I'll request Hemchandran to give once lecture to IST students, at least on digital, that about Bach modulation. You don't find in the Bach modulation in the books. When we were putting IRNSS for Bach modulation, we went around and found out how it does, and it was a big exercise done by SAC and mostly by SAC. I was only the program director. So it was we don't publicize, but you see, Hemchandran, Dr. Mohanlal, they've developed the receiver for PSLV. Okay. Where accelerations are very high, we developed the receiver for satellite, and which the technology was given to Accord Software later on, and Accord Software will start manufacturing it. Then we have changed the Hemchandran, we have changed the code of the IRNSS. We have made a long code of our IRNSS for future IRNSS.
That yet to launch, sir.
Yeah, yet to launch. But that long code we have made it because at the time we were not sure whether this code can be broken or not. But this code was broken the day first satellite was launched.
Because 8 millisecond, no, that's a very short code.
So in Finland, somebody sent me a message that we have broken your code of IRNSS. So that happens. Good.
Yeah.
Thanks.
Sir, this CRP antenna, no, that is one area where we have to put some effort to get a very compact controlled reception antenna, because all otherwise the technology is known and many people has realized. I think ISAC has realized for our satellite application.
Yeah, they are
it's too bulky. Yeah. So definitely we can have a very small form factor CRP antenna.
He's an expert
So
in antennas, and he can use that Devtos Goa sound diffraction.
Sir, that's why I pose the question to the same society. They can really burn the time and find out. See, even Starlink is having 256 element antenna. All are electronically steered ground antennas.
Let's work on this. Let's get the detailed specification and form a small group, and we'll involve couple of students and try to solve the problem with a relatively larger group rather than than individual level. Yeah.
Okay. Thank you very much.
Okay.
Bye.
Thank you, sir.
Bye.
Thank you. I think I'll request the volunteers for carrying out the further proceedings.
Thank you, sir. The Q&A session is over. Now, I would like to invite Arjun, chairperson of IEEE APS GCBH, to present the memento as a token of appreciation.
Arjun, are you there? Otherwise, we'll move.
Let's have a collage group.
Let's have a group photo actually. I request everyone to just put on their video. We can have a virtual photo session at least.
I'd like to request that all participants turn on their cameras for a virtual photo shoot. All of you kindly switch on your camera.
Gomers are online. Namaste.
Okay, done. Now I'm delighted to invite Anu Mohammed Sir, Vice Chair APS Kerala Section and faculty at GCPH, to give the word of thanks.
Anu, are you there? He's there, but he's muted.
Sir, am I audible, sir?
Yeah, it's completely.
Sir, so on behalf of APMTTS, we are really we offer you the gratitude, sir, for having this wonderful session and talking about the significance of GNS and its involvement with other disciplines. I am sure that the students, especially, you could instill an interest in the young minds, and definitely I'm sure that some of them will take up, as our Surendra Pal sir also conveyed, that it's definitely an interesting area, and definitely students will take up, and I'm sure that some of them will definitely work in this area, sir. And I thank all the faculty members and industrialists all over the globe attending this event on behalf of our APMTT Kerala section. I also appreciate the students who from various institutes who are attending this event and urge all of them to take IEEE APMTT membership and get benefited, because our MTTS and APS Kerala sections are doing such events, and please stay tuned with us so that such kind of highly useful technical talks and other events will be happening from our side. So please stay tuned with us. Then I appreciate the efforts of our chapter bearers who are working always supporting, especially the student members who are always at the back end supporting us and making our chapter vibrant. Over to Apren sir for further comments. Thank you, sir.
You're on mute.
Apren muted.
Muted.
You're on mute. Apren, you're on mute.
Oh? Anu?
Sir, over to you, sir, for further proceedings, sir.
You have memento with you?
Sir, actually, memento that day, student day, it's with the student, sir. He will show it, sir.
Okay. Okay. Ramendra, thanks a lot. Thanks a lot once again. And we have a memento to give you that we will be presenting you personally at your residence, or most probably at your residence. So we will be handing over immediately. This is your memento.
Thank you.
So we will be handing over soon. So thanks a lot to all to be present all throughout the session, and it's a wonderful talk. And I am again thankful to Hemachandran, and anyway, he has agreed he will be working with you and give almost all the any suggestions or the any recommendations, any queries you have, and if you want to work with him, he is ready to take you also, give guidelines in technical. So take that opportunity and utilize and be advance in this niche area. Thanks once again. Over to Arjit and Anushara.
Well, I also thank for giving me an opportunity to talk to you all.
Thank you once
Very
again,
much.
everyone.
We'll meet sometime soon. I have never met you. We'll meet.
Thank you, sir. So we are come to an end. Thank you to all of the participants who listened attentively and thoughtfully. To receive your e-certificates, please complete the feedback form in the chat box. Looking forward to the same level of enthusiasm for the next program. Thank you again for everything.
Thank you all.